good morning, good afternoon, good evening from which other part of the world you are. Today we have with ourselves Dr. Benoit Jones. And Dr. Jones has many years of diverse experience in tunneling as a designer, researcher, contractor, academic, and inventor. Yeah. He is a chartered civil engineer and founder and managing director of Inbye Engineering, a technology and consulting company he established in 2014. Before this, he set up the MSc in Tunnel Engineering course, Tunneling and Underground Space course in University of Warwick, and ran it for nearly 5 years. Throughout his career, he has demonstrated a strong commitment to innovation, research, and best practices, writing more than 60 articles and papers. He is the author of a textbook called Soft Ground Tunnel Design and currently chairs the International Tunneling Association activity group on low carbon concrete lining. So it is a pleasure to have you on our webinar platform, Dr. Jones. Over to you.
Thank you very much for the introduction. It's a great pleasure to be presenting to the Tunneling Association of India young members, and I'm guessing a few people from other countries possibly as well. So it's great to see you all. Largest country in the world. India is very important nowadays. So
yes, we are having a lot of tunneling projects coming up, and we're working on a lot of tunneling projects presently as well.
Yeah. I actually just started working with Benoit Consulting, and we have a couple of projects in India, so that's quite exciting.
Yeah.
Hopefully I'll get to go there one day.
Yes, definitely. If you come, you can just ring us up, and it will be our pleasure to meet you in person as well. Our whole committee, Tunneling Association committee, yes.
Great, thank you. Okay, so to introduce the workshop, it's called Soft Ground Tunnel Design. I won't be able to, in just under an hour, tell you everything you need to know about soft ground tunnel design. So I'm just going to focus on a couple of key things. Can't seem to go to the next slide very easily. Oh, let's try it that way. Okay, that's me. So as I said, that's my company, Inbye Engineering, and at the moment I'm also working for Benoit Consulting. So this is the structure of the workshop. So we've done the introduction. I'll do a quick tour of the textbook, just so you get an idea of what's in it, and then going to focus on stability, which is the most important thing in tunnel design, and it's the thing that pretty much drives all your decisions about what construction method to use. And we'll look at collapse and blowout, and then undrained and drained stability with a couple of examples, and then there'll be conclusions and time for some questions at the end, hopefully. So this is what the book looks like. You can get it as softback, hardback, or ebook, or whatever. I say it's the first ever textbook written on soft ground tunnel design because although people have written books, I don't think any of them has been kind of comprehensive or has included worked examples. So I'll show you what I mean. So each chapter starts with learning points, like what you'll understand and what you'll be able to do at the end of a chapter. It then has what I call teaching, which is, the text, the figures, the photos, tables, derivations of equations. And then there's worked examples that show you step by step how to do it. And I actually found when I was doing the worked examples that I then had to change the teaching bit, because it's only when you try to go through it step by step that you realize, oh, that bit of information needs to be presented, and oh, you need to make clear that assumption and things like that. So I think that actually improved the writing of the book quite a lot. And then there's a summary which recaps the learning points. And then at the end of each chapter, there's problems to enable you to practice. And I'd say, like most books and papers on tunneling, just do that bit, and they don't do all the rest. So there's I assume you've all, when you've found a journal paper or a conference paper about a subject you're interested in, but then you find, oh, there's missing steps in here, or it doesn't set out in a worked example how I'm meant to do it in the way they've done it, or to apply this knowledge. So hopefully this kind of textbook is filling a gap there. So there's lots of chapters. Starts off with real tunnel behavior, then undrained stability, drain stability, stability of shafts, stability and Eurocode 7, which kind of, although it's European, it's kind of showing how you apply partial factors in different limit states. So it's kind of an example of that. And then there's global design using analytical solutions and using numerical modeling, lining materials with particular focus on fiber reinforced concrete, and segmental lining design, segment design for transient loads, like all the demolding, handling, stacking, transporting, loading, jacking and grouting pressures and everything except like the chapter 9 is about the sort of ground and groundwater pressures on the lining, and chapter 10 is everything else before that point. And then chapter 11, sprayed concrete lining design. Chapter 12, estimating ground movements. Chapter 13, estimating building damage. So you can kind of see they're grouped. So chapters 2 to 5 are on stability. 6 to 11 are soil structure interaction and the structural design of the lining. 12 and 13 are ground movements. And chapter 1 is really everything, because it, using real case studies, it shows data about ground movements around tunnels and surface settlements and subsurface movements and lining stresses and strains and deformations. And so the idea is to give the reader a conceptual model in their brain of what is going on when a tunnel is being constructed and then into the long term. So it sets you up for then understanding the rest of the book after that. So inside the book, there's lots of nice pictures of, that's in chapter 1, showing lots of case studies of things moving. Yeah, so a lot of the pictures I drew myself. And then you can see on the left, there's worked examples. Usually they're in grey boxes, so they're sort of separate from the text. There's problems at the end of each chapter. And then there's also references, and at the back of the book's an index. So you can use it either as, you can read the book cover to cover, as one of my colleagues did. Or you can just, read a chapter you're particularly interested in, or you can go into the index and say, oh, I want to know about, for instance, the convergence confinement method. Where do I find that? And then you can see which pages that's on and find all the references to that. So use it like a reference book. Okay, so that's enough about the book. So I'm going to talk for a while for the rest of the time, basically, about stability. So when we're talking about stability, it could be the collapse of a tunnel, and that would have often serious consequences, particularly in urban areas. So there on the left, you can see the Sao Paulo metro collapse. So that was actually the tunnel collapsing near to the shaft, and then part of the shaft collapsed as well after that. And then on the right, you can see Munich metro collapse, where actually a bus fell into the hole and 2 people died and 30 people were injured. That was in 1994. With stability, there's also the problem of blowouts, which is kind of the opposite of a collapse. It's when you've got too much internal pressure in a tunnel. So there's two main types of blowout. There's a kind of passive failure. So, like with a retaining wall, you could fail a retaining wall due to active pressure, or if you push the retaining wall into the ground, you could fail the ground behind it in a passive failure. And that's kind of what's happening. So if you see this sort of diagram on the right, this was from Benoit et al. In 2012. They did a model of an EPB, that's an earth pressure balance machine, in a laboratory. And they were pushing it along, and then they just stopped excavating and basically just pushed it into the ground and measured how it failed. And so a passive failure is like a sort of upward moving rigid block. You need quite high forces, especially if the tunnel's deep. You need very high forces to make that happen. So it's kind of a little bit unlikely. We don't see it very often. Another possibility is hydraulic fracturing. So in hydraulic fracturing, that's where a fluid, which could be compressed air or it could be slurry or water in the head of a machine, is under too high a pressure, and it literally fractures the ground and escapes down the path it creates. So hydraulic fracturing usually occurs at lower pressures than passive failure, but it only happens when there's fluids in the face of the machine. On the bottom left here, you can see a passive failure blowout. That was due to excessive compressed air pressure during construction of the Docklands Light Railway Lewisham extension in 1998. So they wanted to build this cross passage right under the River Thames, 27 meters of waterhead. So they needed about 2.7 bar to counteract that and build that cross passage. So they put a bulkhead just Inbye of it, and then one near the portal. And then they were testing the compressed air bulkheads. And when they were testing the bulkheads, they kind of hadn't done the calculations to check that there was sufficient cover over the tunnel at the shallow point. And it literally blew the segments and the ground up and out. And there's a picture here, and you can see a huge crater. Just the soil's just been blown out by the air pressure. And it's in the grounds of the school. And you can see the building behind. A lot of the windows have been broken. Luckily, it was at the weekend. You can imagine if it was during a school day, it could have been a huge disaster. So blowouts are also important and shouldn't be forgotten. But for the rest of this presentation, we're going to focus on collapse. It's kind of a bit more common. So collapse mechanisms. So it's always important to start with understanding the geology and the hydrogeology, and then thinking about how could this fail. So as engineers, that's always how we design things. We think about how something's going to fail, and then we kind of apply safety factors and make sure it won't happen. But we always have to do that first step of identifying what are the failure mechanisms. So there could be a large-scale stability failure, like the ones we've seen, like in Munich or the DLR. You could have a hydraulic failure, and that's just, sort of running sand or running ground. So where the seepage forces in the ground are just taking the soil grains with it. And that usually happens in cohesionless soils, like silts, sands, and gravels. And literally the flow of the groundwater just takes the soil with it. Or you could have a sort of block failure, particularly in sort of stiff fissured clays, which, is similar to a block failure in rock. It slides on discontinuities. So here we've got a picture of an inrush of sand and water under Green Park. This is in London in 1964. So it's using a drum digger shield, which is basically like a steel can, a shield, with a cutter head on the front, but there's no, it's not a closed face machine. It's basically an open cutter head, and the cutter head just cuts the ground and loads the ground onto a conveyor belt. So, so what happened was they just got the layer of clay above the crown just got a bit too thin, and it broke through with an inrush of sand and gravel. So that's kind of a little bit of a mix of failures, but you can see in this case the face was completely stable, but it just came through at the crown. So that was more of a hydraulic failure. So literally the flow of water into the tunnel just brought the sand and gravel with it. We had the Munich Metro collapse, and that was kind of similar, where the tunneling was in marl, and this was conventional tunneling with sprayed concrete. And the marl is quite competent, quite impermeable, but above the marl is gravel right up to the surface pretty much, and it's about 15 meters thick of gravel. The groundwater level is quite high within that. So where the marl just got a bit too thin, it failed, and a load of sand and gravel came into the tunnel. Here we've just got a video, and this is just in London, and it's just an inspection of a tunnel. You can see it's an old cast iron tunnel. Got about 30. And outside of this tunnel lining is a sand channel, which when they built the tunnel in the 70s, yeah, you can see yeah, when they built the tunnel, the groundwater level was lower, so it was actually kind of dry. So it was pretty stable, but now the groundwater level's increased. And so just through that 30 millimeters diameter hole, the sand and water just will flow out of it. So that could be a big problem. You imagine if you had that in the face of your tunnel, starts flowing in, there's not a lot you can do about it. So sort of running ground is a big risk in tunneling, especially with open face methods. And we always need to deal with it. Either you kind of dewater or depressurize it so that there's no seepage anymore, or you freeze it or you grout it. But it will, if there's groundwater pressure in no cohesion, it will just flow like a fluid through even very small gaps. Sometimes we have a mix of mechanisms. So I'm looking at an example right now where a sand layer, it's a big tunnel where they were using canopy pipes, and there's a sand layer just near the canopy pipes, and the sand layer flowed in, and then that sort of undermined the bearing capacity of the canopy pipes, and then the canopy pipes and the face and the overburden all failed into the tunnel. So you can sort of have a hydraulic failure followed by a stability failure, or other combinations. So with stability, there's four main factors that influence stability. So first we have cohesion and support pressure, which improves stability. And we have gravity and seepage forces, which worsen stability. In undrained soils, which pretty much is clays, seepage forces are negligible. So we just ignore them really. So when is a soil drained or undrained? A rule of thumb is that a soil with a permeability less than 10⁻⁷ to 10⁻8 meters per second will behave in an undrained manner during the timescale of a typical tunnel construction, and a soil with a higher permeability will behave in a drained manner. So if you were in that sort of range, 10 to the minus 7 to 10 to the minus 8, you'd probably try and do calculations for both the undrained and the drained case, and then, you know, design to the worst case, basically. So drained and undrained stability are very different in both geometry and kind of mechanism. So the calculations are done in a different way. So here we've got the geometry of a stability failure in clay and in sand. So on the left in clay and on the right in sand. And you can see that with clays, we tend to get a large cone-shaped failure. And in sand, we tend to get a very vertical, steep-sided chimney failure. So for undrained stability, we tend to simplify the geometry of a tunnel heading like this. So we've got Z0 is the depth to the tunnel axis from the surface. We're tunneling here left to right. We have an unsupported length P. In a closed face TBM, we'd probably take that as 0. We've got C, which is the cover to the top of the clay, and D, which is the excavated diameter. For a sequentially excavated tunnel lined with shotcrete, some assumptions about the value of P may need to be made. Like for a top heading, we often take P to be sort of the advanced length plus a bit to allow for over excavation. For non-circular tunnels, the diameter D is chosen to give the same face area. So basically, you have the face area of your non-circular tunnel, and you work out what's the equivalent circle diameter, and then you use that as the value of D. So actually, Chris Pound did a load of parametric analysis and showed that the shape doesn't really matter, that it makes very little difference. And Z0 is taken as the depth from the surface to the centroid, and C is always, even for a, you know, even where you're using an equivalent diameter, you always take it from the crown of the tunnel to the top of the clay. Broms and Benoit in 1967 defined a stability ratio N, which is the ratio of full overburden pressure at the axis of the opening minus any support pressure and divided by the undrained shear strength of the soil. So we've got N is the stability ratio, and it's dimensionless. Gamma is the bulk unit weight of the soil. Z0 is the depth to axis, as we saw on the previous slide. So gamma Z0 is the vertical total stress at the axis level of the tunnel. So this is kind of the effect of gravity, well, plus the sigma S is the surcharge. So these together are the effect of gravity. And then we're doing minus sigma T. Sigma T is the internal face pressure. So if you are applying one, if it's a conventional tunnel, no compressed air or anything else, then it would just be 0. And Cu is the undrained shear strength. So we've kind of got destabilizing actions on the top and the sort of undrained shear strength at the bottom. So N is just a dimensionless number, and a higher value of N is less stable and a lower value is more stable. So we can see just by looking at the equation, if we increase the undrained shear strength, N reduces, and that means it's more stable. If we increase the support pressure, sigma T, N reduces, more stable. Increase the surcharge or the overburden pressure, then the tunnel becomes less stable. So we can define a critical stability ratio, which is the value of stability ratio at which collapse occurs. And we call that NC, or critical stability ratio. And Robert Mayer in 1979 performed a suite of centrifuge tests of a tunnel heading in clay at different C/D and P/D ratios, and basically drew some design curves based on that data. So it's very much an empirical relationship. So if the stability ratio N is bigger than the critical stability ratio NC, failure occurs. So the ratio NC over N is the factor of safety for heading stability. If NC over N is less than 1, the heading collapses. Using the German guideline for face stability, we might require NC over N greater than 1.5. So we want a factor of safety on collapse of 1.5. That's similar to, there's a Hong Kong guide to slurry tunnel boring machines, and that also says 1.5. So it's not just the Germans. So also you can see on the right, I've plotted all the centrifuge data, which is the circles, for P/D is 0, which is 0 unsupported length, and P/D is infinity, is basically an unlined tunnel in clay, which doesn't happen much in the real world, but it's there. They also did centrifuge tests for different values of P/D ratio in between, but they weren't for exactly 0.51 or 2, so I didn't plot them because it'd be confusing. There's also a couple of real tunnel collapses here for quite small C/D ratios. So yeah, there's quite a good bit of empirical data to support the curves. So again, like if we have a lower value of critical stability ratio, that means it's less stable. So you can see each of these curves is for a different P/D ratio. So as you increase the unsupported length, then the stability gets worse. Also, if the C/D ratio increases, stability improves because the critical stability ratio goes up. So we can, by increasing the clay cover above our tunnel or reducing the diameter, we can improve stability. So here I've got a worked example. So I'm going to try and use my special pen on my screen. So we've got a tunnel that's 10 meters diameter. The depth to axis is 20 meters. The undrained shear strength is 50 kPa, and the bulk unit weight is 20 kilonewtons per cubic meter. And this is a very simple example. It's all clay and it's all got the same undrained shear strength. In reality, things are a bit more complicated, but we'll try that just to give an example. So we need to use this equation for the stability ratio and this chart. So going to start with, first we need to know what C is, the cover. So C is Z0 minus half the diameter, which is 20 minus 5, so it's 15 meters. So the C, oops, something went wrong there. Okay, we're back. The C/D ratio is 15 over 10, which is 1.5. And we said it's a earth pressure balance, TBM, so P is 0, so P/D is also 0. So we can look up on the chart, we can find C/D is 1.5, is about there. P/D is 0, so it's about there. So the critical stability ratio from the chart is about 6.8. always got to be careful that it goes up by 2 each time on the y-axis of the chart. So we also need to calculate equation 1, which is the stability ratio n. So n equals gamma times z0, so that's 20 times 20. Plus there's no surcharge, so that's just 0. So at first we're just going to assume there's no face pressure, so we'll just say that's 0 as well. Sigma t divided by Cu is 50. So that's 400 over 50, which equals 8. So you can see that this fails because NC divided by N is 6.8 over 8, which is 0.85. And for us to be safe, we need it to be over 1, or actually over 1.5 to have a good factor of safety. So to find, if we wanted to know what face pressure we need to apply, what value of sigma t, then what we can say is, okay, we need the NC divided by N to be equal to 1.5. And if we rearrange that, we know what NC is already. So we need N equals NC over 1.5, just rearranging that equation, which is 6.8 divided by 1.5, which is 4.5. So then we can use that equation. So we can say 4.5 equals the gamma z0, which was 400. Surcharge was 0, and then minus sigma t all over Cu, which is 50. And then, if we rearrange that, we end up with sigma t equals 175 kPa. So this is telling us that if we want a factor of safety of 1.5, then we need to apply an EPB pressure, an average EPB pressure of 175 kilopascals. Okay. So one question we could ask, what if there's a coarse grain soil overlying the clay, so it's not all clay to the surface. In many places we are tunneling in clays, we have sands, gravels on top in sort of river basins and things. So this was investigated in a limited way by Grant and Taylor using centrifuge tests, and they showed that for loose sand overlying clay, the sand can be assumed to act as a surcharge. There may be some benefit to stability from denser sand, but this is difficult to quantify from their data. So therefore, what we do is we just we take the cover C to the top of the clay, not to the surface, and then we just count the overlying granular deposits as part of the surcharge. So if you look at this equation, whether we include it in sigma s or as gamma z0 kind of doesn't matter. It's just the overburden pressure. But we should take C in the C over D ratio for reading the critical stability ratio as the cover to the top of the clay. So by kind of taking the cover just to the top of the clay, that's less than taking it to the surface. So that's worse for stability. So having 10 meters of clay above your tunnel is better than having 5 meters of clay and then 5 meters of gravel. It's more stable to have more clay above your tunnel. That's the answer. So in summary, undrained stability can be assessed by calculating the stability ratio N and comparing it to the critical stability ratio NC in MES design chart. And the factor of safety is given by NC divided by N. Stability can be improved either by increasing NC or by reducing N, which can be achieved by reducing the diameter. So make the tunnel smaller, then that will increase the C/D ratio. We can increase the cover, that also will increase the C/D ratio. We can decrease the unsupported length, that will make the P/D ratio go down. So we're going up in this direction, which is good. We can decrease the depth or the surcharge pressure in this equation. Or we can increase the support pressure applied sigma T. We can increase the undrained shear strength. We, don't always, but we could do that by ground improvement, for instance, or by relocating the tunnel. So this is a weird thing that I said that if you look at the equation for N, if you make it shallower, then N is reduced and therefore the tunnel is more stable. But a shallower tunnel has a lower C/D ratio, so it's less stable in terms of the NC value's gone down. So the N value goes down, but the NC value also goes down. So the net effect kind of balances out. But usually a deeper tunnel, as you go deeper into clay, usually the undrained shear strength increases with depth. Obviously, you have to check that with the site investigation and the data you have. But if it increases with depth, then usually you have better stability as you go deeper. You could also use pre-support measures like canopy tubes, spiling, or face dowels. In a sense, these are kind of qualitatively reducing the unsupported length or applying a support pressure or reducing the overburden pressure. You can't easily include them in this model, so there's no way to quantify that using this method. There are other methods you can use to kind of do that, but they're more sophisticated methods. So now we've sort of finished undrained stability, and we're going to look at drain stability. And again, like the same four main factors influence stability, whether it's drained or undrained. So cohesion and support pressure improve stability, and gravity and seepage forces worsen stability. So, and remember that, undrained materials, large cone of failure, drained materials, steep-sided chimney failure. In drained soils below the water table, seepage forces are important. And stability of a tunnel face in a drained soil does not depend on depth, except when it's quite shallow. Small amounts of support pressure or cohesion can improve stability a lot. But even a small head difference can worsen stability. So the method that is most widely used is this kind of limit equilibrium method by Anagnostou and Kavari that they attributed to Horn. And they developed it to allow direct calculation of the required support pressure in any situation above or below the water table, with or without seepage, for tunnels where P equals 0. You can sort of adapt it for small unsupported lengths. We won't go into that right now. So you can see it's like it's a sort of face wedge, which is kind of triangular prism. And then there's a silo above it, which is a rectangular prism. So you can have, so what it does is you calculate using silo equations. You calculate what's the silo pressure on this surface CDEF, and then you calculate the equilibrium of the face wedge. So you have to apply a support pressure usually to get that equilibrium. And you vary the angle omega here. So the angle of the face wedge, you vary that to find the worst case. So in a sense, you're seeking the worst geometry. And it looks a bit weird because you got a circular tunnel, but the intersection of this wedge prism model is square, but it seems to work pretty well. So you can see on this graph, this upper dashed line is this wedge prism method, and here's some 1G laboratory tests in triangles. So you can see it's predicting the y-axis is support pressure that's normalized by gamma d. So you can see it's predicting a slightly higher required support pressure than what the laboratory tests are predicting. So it's sort of on the safe side. Some of the other methods like Lecker and Dormier's upper bound or finite element method calculations are on the unsafe side. And that's what we often find with numerical modeling of stability, is that it does tend to be on the unsafe side. So you need to be careful when using numerical models for stability of tunnels. So Anagnosto and Kavari defined 4 dimensionless coefficients, F0, F1, F2, and F3, which can be read from nomograms. So they did this to make it easier for practitioners. So there's this equation, which is S dash is the effective support pressure required to prevent collapse. So that's the support pressure you have to apply to the soil grains. F0, F1, F2, and F3 are dimensionless coefficients. Gamma dash is the submerged unit weight if you're below the water table. So it's the bulk unit weight minus the unit weight of water. C dash is the drained cohesion, and D is the diameter of a tunnel. Delta H is the head difference between the in situ groundwater head H0 and the head in the excavation chamber HF. So delta H is H0 minus HF. So it's the head difference that is going to drive seepage towards the face of the tunnel. So you can see these are the nomograms that will give you F0, F1, F2, and F3. So you just need to know something about the geometry of your problem, the H over D ratio. You also need to know the friction angle, and you need to know the position of the water table. So when H0 is equal to H plus D, that means the water table is at the surface. H0 equals 1.5 D is when it's half a diameter above the tunnel crown. So they've only given you 2 different kind of examples. So if you wanted to use this for something that's very different, then you can just use the equations. So in my book, I've derived all the equations for the F0 and F1 nomograms. So you can use any position of the water table. And you can even split your silo up into different layers. There's lots of things you can do if you understand the basic equations behind this, which are fairly straightforward in the end. But the easiest way is to use the nomograms, which we'll do just for an example today. But first we'll just look at so how a slurry machine works, because it's actually the simplest example of drain stability is a slurry machine. So the slurry TBM supports the ground by filling the head with bentonite slurry under pressure. The slurry pressure must be greater than the groundwater pressure, because otherwise it would not be possible to pump it into the head of the machine. But also because we need an excess slurry pressure to apply an effective support pressure to the soil grains And then we also need to include an allowance for variability, which I'll talk a bit more about in a minute. So you can see here, if the dashed line is kind of the water pressure gradient down through the soil. So if we have a slurry pressure that's higher than that, which we need, then this excess slurry pressure is hopefully going to apply pressure to the soil grains themselves. Because you imagine that the slurry pressure up to the water pressure, all that's doing is just counteracting the pore pressure in the ground. So you need a higher slurry pressure than that to then start supporting the soil grains. If you just applied the water pressure, then the soil grains would just fall down if there's no cohesion in the soil. So the exact mechanism by which slurry applies a pressure to soil grains in the face of a TBM is quite complicated, but it more or less boils down to it kind of infiltrating into the pores of the soil, kind of blocking those pores to some degree, and then, you know, having a pressure gradient close to the surface of that soil. So you can actually lose stability over time as slurry infiltrates into the soil. So if you stop for too long and you've got a reasonably permeable soil, the slurry starts infiltrating, and then you're not applying the excess slurry pressure directly at the face. It's kind of spread into the ground over a gradient over a distance. And as it spreads further and further into the ground, the sort of effective support pressure goes down. So during stoppages, you often have to increase the slurry pressure and or increase the viscosity of the slurry to stop it infiltrating so quickly. So another thing to point out is that the slurry pressure increases with depth faster than the water pressure does, because slurry is a little bit denser than water. So when we do slurry pressure calculations, we always do it at the crown, because we know that if we do it at the crown and it's okay, then lower down it will be even better. So we just calculate things at the crown. Now imagine if we had a slurry pressure that was much higher than what's shown here, and so that it kind of would have a gradient that crossed the surface. Then you then need to be careful about, one thing is hydrofracturing the ground, hydraulic fracturing. So you need to check that with the ground soil parameters that you have. But also, if you were to encounter an abandoned well or an abandoned borehole, then with that slurry pressure, you would basically have slurry coming out at the surface, which might not be good. So yeah, just need to be aware. And this is why there's been a development of variable density slurry machines, so that you can increase the density of the slurry. And if you increase the density of the slurry, you kind of make this a steeper slope so it doesn't intersect the surface. So you're less likely to have those problems. But always when we're setting slurry pressures or any kind of face pressures, we always need to calculate what's the minimum we need to ensure stability against collapse, and then what's the maximum we need to not have slurry leaking out somewhere. So all slurry machines experience fluctuations in the slurry pressure due to dynamic effects such as rotation of the cutter head, excavation and pumping, and due to the difficulty in balancing the slurry feed in and the slurry extraction rate out. Having a mixed shield machine with an air bubble kind of helps with controlling the pressure a bit, but there's always going to be a plus or minus number. And since a drop in the slurry pressure could result in instability and hence over excavation, an allowance for variability is added to the target minimum face pressure. Sometimes a factor of safety of some kind is also included, as well as an allowance for the effects of surcharge on the surface. So this is the equation. So PST is the target minimum slurry pressure. S dash is that effective support pressure that we got from the nomograms from Anagnosto and Kovari. U is the pore pressure in the ground in kPa. And usually if we're calculating the slurry pressure at the crown, so calculate U at the crown as well. And V is the allowance for variability of slurry pressure. So typically in a very well-controlled mixed shield slurry machine, it might be as low as plus or minus 10 kPa, in which case you would add 10 kPa to this. But in a sort of more traditional slurry machine or one that's not very well controlled, it might be as much as 30 or more kPa. Q is an average surcharge pressure applied to the surface. So yeah, if you're using the actual silo equations, there's ways in which you can include the surcharge in that, and then it actually has less effect and it's kind of more efficient. But otherwise you would just add it here if you were using the nomograms. So partial safety factors should also be applied. I haven't included them here, but see the DALB for details. Usually there's a partial factor on the pore pressure. There's also one on the effective support pressure in the other direction, and also on the surcharge. Okay, so I've got a worked example. So I'll quickly go through this. So here we've got surcharge of 75 kPa. All the ground is sand with a bulk unit weight of 18 kilonewtons per cubic meter. The cohesion is 0 and the angle of friction is 30 degrees. We have an allowance for variability of 25 kPa. So it's the slurry machine. We have a cover H of 15 meters and a diameter of 9 meters. And the water table's at the surface. So from this equation, you can see that actually if the cohesion is 0, then basically that term is 0 and that term is 0. And if we're using a slurry machine and the face pressure, the slurry pressure is higher than the groundwater pressure, then we don't have delta H. So that's 0 as well. So we can just use the first term. So first we need to use the nomogram. We need to know H over D, and H over D equals 15 over 9, which equals 1.67. And in our example here, H naught is the distance from the invert up to the groundwater level, as you can see on the nomogram as well. So in our case, H naught is equal to H plus D. So we're going to use the dashed lines here. So reading off from the chart, we have a friction angle of 30 degrees. So we're over here. And we're using the dashed lines sort of 2/3 of the way between the 1 and the 2. So there's the 1 and there's the 2. But you can see that at 30 degrees, it doesn't make a lot of difference. If we had a silt, for example, with low 20s friction angle, it would make a bigger difference. But in our case, F naught is about 0.22. So then we can use this equation for S dash. So S dash equals F naught times gamma dash is submerged unit weight. So it's the bulk unit weight minus the unit weight of water. and then we've got times D, and D is 9 meters. So it's 0.22 times 8 times 9, which is 15.8 kPa. So if we were calculating the slurry pressure we need at the crown, so the pore pressure at the crown is equal to the head at the crown times the unit weight of water, which is 150 kPa. So it's 10 times more than the effective support pressure. And that's often the case. So PST, target minimum slurry pressure, is it's S plus U plus Q plus V, which is 15.8 plus 150 plus the surcharge 75 plus the variability 25, and that all equals 265.8 kPa. So that's our target minimum slurry pressure. It's quite, using the nomograms makes things quite simple, but as I said, you can use the actual equations. It's much more satisfactory to use the actual equations. More fun if you like maths. Yeah. Okay, so in summary, just to sort of summarize maybe like the key things I wanted to communicate today, just finishing now, so good timing, eh? So it's really important to understand the geology and the hydrogeology and think about the potential failure mechanisms, and beware of running ground. Wherever you've got cohesionless soils below the water table, just think, oh, these will run if I don't do something to either depressurize or take out the water or give the soil some cohesion by grouting it or applying a support pressure. So always remember 4 main factors influence stability: cohesion and support pressure improve it, and gravity and seepage forces make it worse. So any questions? I can see there's some questions in the chat.
Thank you very much, Dr. Johns. There is one question from the audience. I'd like to read it out loud to you. How to predict a slurry pressure if strata above the groundwater table is fragile and collapsible? I mean, is it required to consider cover up against the ground surface?
Yeah, I'm not sure what is meant by fragile and collapsible. Okay. So you can, the slurry pressure you need is based on, you know, what you calculate is what's the effective support pressure I need to support the soil grains in the face. Sorry, is someone talking?
No, it was just a disturbance. You can just continue.
Okay. So then you know you need to basically have the slurry pressure has to be whatever the pore pressure is in the ground, plus you need to have an effective support pressure to support the soil grains in the face to hold the soil back as well. And then you need, you know, an allowance for variability and for surcharge and all those things. So your slurry is always penetrating into the ground. I'm not sure if the strata above the groundwater table is fragile and collapsible. I'm not sure what the questioner is asking. Maybe they can clarify if they're online.
Sure, Dr.
Are
Johns,
you
we will
online?
share.
Hello, yeah. Hello.
Hello.
Hello. Very good evening. Actually, my question was like fragile means to say the ground is rocky, but it's having the GSI less than 20, means kind of soil, kind of strata. Like sinking
Okay.
may take place, like gravels, that kind of thing.
Mm.
Like shear zone may exist. If my the layer is like sandwich,
Okay. So I
means
think,
the failure will be extend up to surface,
yeah. So
I guess. Yeah.
yeah, I guess if it's just yeah, very sort of
But again,
disintegrated down to gravel, then
yes, yes. But
sort of treat it like gravel, maybe. I think need to be a little bit careful because sometimes like weathered rocks or damaged rocks are kind of the rock parameters, you know, in terms of cohesion and angle of friction are sometimes sort of based on confined pressures in the test and need to be sure that you really do have cohesion. So yeah, it might be safer to assume there's no cohesion. If it's really just, you know, fragments of rock, then there should be zero cohesion, really. Yeah.
sometimes there may be chance like some loose pocket may occur while the urban tunneling. There may be the loose pockets. So the means
Mm.
the collapse may take place. Anyway, we do grouting for the same.
Yeah, I think, well, you certainly wouldn't treat it as undrained soil. So if your tunnel is in clay and there's that kind of material above it, then you treat it as a surcharge. Otherwise, you'd use, you know, if that's in the face, then you'd use the drained calculation to assess the stability. Yeah.
Okay, thank you. Thank you.
Yeah.
Thank you very much, Mr. Abhijit. And personally, I also have a question regarding the same. How do we do calculation in the conditions like a rapid drawdown condition where it was in drain state and suddenly draw down to the a completely undrained state to the drain state? It's a very rapid behavior. In that case, do we have to take any such precautions?
You mean rapid drawdown during construction?
Yes, yes. If there is a sudden incident and the rapid drawdown of the water table, so the pressure is.
Yeah, it depends what tunneling method you're using. So yeah, if you're using a closed face machine like a slurry or an EPB machine, then you know that a rapid drawdown of water pressure in the ground for some external reason would not be a problem necessarily. It would make it more stable. If it's your tunnel that's drawing down the water, then that could be a problem because that means you've got a lot of seepage towards your tunnel, and that seepage could be destabilizing.
Oh, okay, okay. Thank you very much. And personally, we would love to have a hands-on experience on your book, and we would love to have another workshop with you again, just like an ICE workshop. Well, thank you very much, Dr. Jones, for a wonderful webinar on soft ground tunnel design. And I'm sure that I see there are two more questions are there. We will take those first.
There's a couple in the chat
If it's
as
not,
well. Mm.
yes, if it's not a problem, we'll take two more questions.
Okay, are they the ones in the chat that I can see?
Yes, yes, sir. Yes, sir.
Yeah. Okay, so the first one is how to evaluate stability equation for the Natum case, as there is no pressure in it. and how to calculate in case the strata is partly rocky and partly soil. So yeah, there's always tricky situations. So if you literally had the bottom half of the face is very stable rock and the top half is soil, then you could just take the face as the top half and just assume the bottom is stable, right? So you just take the face area as the soil face area and do it that way. So for the NATAIym case, as there's no pressure, yeah. So if you've got a drained soil, so sand or gravel, you can't do a NATAIym tunnel below the water table in sand or gravel that doesn't have cohesion, because it will just collapse. There's just no chance. But if you're above the water table, then it might stand up a bit, you know, if it's moist and if it's got a tiny bit of cohesion, it might stand up. If you just do pocket excavation, if you use pre-support like spiles or canopy pipes to help support it, then you can probably excavate it and support it. But you have to be really careful that you don't have perched water tables or, you know, it's fine until the monsoon begins and then the water level goes up or there's a lot of infiltration from above. So you have to be very careful. So in the case that you have sand or gravel in the face in a NATAIym excavation, and you're below the water table, you really can't do it unless you use ground freezing or grouting, or you take the water out of the ground. So you make sure there's no water pressure in the ground by either from the tunnel or from above or somewhere else. You drill ahead of the face and you make sure you suck the water out of the ground or depressurize it at least, using vacuum pumps or whatever you need to use. So really, that's the solution. And at the extreme, people have jet grouted all the sand and gravel in the face before they've excavated it. So the other question is, can you comment about computing drain stability scenario while doing excavation by NATAIym method? It is a little bit more tricky. So you can include an unsupported length. If your ground has got some cohesion, then it might stand up in the calculations. If it doesn't have cohesion, then you start needing to take account of pre-support measures and other things. So there are ways, if you use the silo equation, you can then sort of calculate what's the silo pressure on the top of the wedge based on with the presence of canopy pipes. So you can calculate what that is. You also need to design the canopy pipes to take the load, and they need to extend far enough ahead that they're resting on stable ground ahead of that disturbed kind of face wedge. Yeah, it can get very complicated. But yeah, it's always true that if you've got no cohesion in the ground, it will collapse. You know, like you need a sand. If you're on the beach playing and making a sandcastle, it needs to be a little bit damp for it to stand up at all. If it's saturated, it's a mess. If it's completely dry, it won't stand up. So just think about that. If you want to have a face in sand or gravel or silt and there's no cohesion, then you really need to have no water pressure, and you can only expose small areas of it at a time, and you need to protect the perimeter using spiles or canopy pipes. And you probably need to sort of buttress the face and spray the face immediately with shotcrete. So you just do little pockets and you spray the face. but really it's a sort of case-by-case basis. And alternatively, you just grout it all up or freeze it all. They're the other alternatives. Okay, I think another question has just popped up, but do we still have time?
Yeah, we can continue. It's up to you. If you have time,
Yes, we can
take
continue.
questions. Yeah.
So the question seems to be about drill and blast tunneling. So if you're doing drill and blast, then it's basically rock, which is not really the subject of my presentation, but yeah, I think the answer is yeah, 15-meter wide by 8-meter high D-shaped tunnel in rock that is strong enough to need blasting, but it's heterogeneous. I don't know. The feasibility depends on the quality of the rock and the discontinuities and, you know, an assessment of all that. But there'll be a way to do it. Okay. So I think we're done.
Yes, I don't think so. There are any more questions. Once again, thank you very much, Dr. Jones, for a wonderful webinar on soft ground tunnel design. I'm sure that experience will be very useful for everyone, and how I hope our student members have got a clear idea of the today's topic. I would like to inform all that our past webinars are available on our YouTube channel, and this webinar will be uploaded very shortly. If you are not a member and want to become a member, please kindly contact for the details. Before signing off, I would like you to request all members to renew their membership for the year 2024 to ensure the timely benefits. I would like to invite new members to the part of TAIym, which is solely focused on bridging the experience of professional working in a different projects and also act as a platform to share technical expertise in the field of underground construction. And there are always many additional benefits of being a member. So grab a chance of being one. Once again, thank you, Dr. Jones, for sharing your experience, and thank you all for joining. Have a great weekend. Stay safe and happy tunneling.
Okay. Thank you very much.
Thank you, Dr. Jones. But I just want to add that we would really like to have a workshop, like you said, you have with IC. So we'll like to have it soon with you. So our
Okay, that's just a sort of a longer version of this. It's about twice as many things, and there's more examples.
Yeah, it's good that our the people will be able to solve the questions as well. They'll have a hands-on experience as well.
Yeah, it's like a half-day thing.
Oh,
yeah,
it's
we
a
can do that.
thing.
Yeah.
Let's plan. We'll just have a poll inside our thing, and let's see if the members, because it's online, right? And I think in IC you do it physically. So
yeah, last time was physically. The time before that it was online actually, and there were a lot more people, obviously, because like the in-person one was like limited by the size of the room. So yeah.
Yeah, it was a very informative webinar. Thank you, Dr. Jones, for accepting to speak on our platform. And
okay, well, thanks for having me.
Yeah.
Bye. Thanks.
Okay.
Bye-bye.
Bye.
Thank you.
Have a nice day ahead.